Hello and welcome back. In the last few sessions, our discussions were centering around the concept greatest common divisor or GCD. We derived an important identity called Besso's identity, and after that we derived a most important theorem in elementary number theory, the fundamental theorem of arithmetic. Now we are moving towards an analogous concept known as least common multiple or LCM. In this session, we are giving the definition of LCM and we are going to see a few properties of LCM.
From the word LCM, it is clear that we are trying to find out common multiple of two given numbers and then the least among the common multiples. An important question here is that suppose that we are given two integers or two positive integers a and b, and definitely we can find multiples of a and b because we can take 1a, 2a, 3a, etc. and then 1b, 2b, 3b, etc. So multiples of a and b definitely exist. But what is the guarantee that common multiples of a and b exist and we can find a least element among that? So we should initially explain that why should the term least common multiple actually makes some sense. We are going to do that right now. The first question that we are going to ask is this: least common multiple or LCM, why should it exist? Okay, we are starting with two positive integers a and b. Let a and b be two positive integers. Can we find multiples of a and b? Of course. In fact, positive multiples. Suppose multiples of a, we denote by the set MA, and that consists of 1a, 2a, 3a, etc. These are multiples of a. Similarly, multiples of b also we can list like this: 1b, 2b, 3b, etc. Now the question is, can we find the intersection of these two sets to be non-empty? Of course we can find the intersection, but what is the guarantee that the intersection is going to be non-empty? And then only we will be able to take something common. Note that b is a positive integer and a is also a positive integer. Therefore, one multiple of a will be actually BA. BA is in MA. That's clear. Now, one multiple of B is AB. AB is in MB. Therefore, MA and MB has at least one element in common, that is AB. Therefore, MA intersection MB contains at least one number. So we can discuss about the least element or a least element in MA intersection MB. So what about the least element in MA intersection MB? Not that a is a positive integer and we are taking only positive multiples. B is a positive integer, we are considering only positive multiples of B. Therefore, MA and MB consists of positive integers. Therefore, MA intersection MB also will consist of only positive integers. Therefore, MA intersection MB is a subset of the set of all whole numbers, and MA intersection MB is not equal to 5. Therefore, we can apply the well ordering principle in the set of all whole numbers. Therefore, by well ordering principle, we have there exists a least element in MA intersection MB, and we call this as the LCM of A and B, and denoted by, we used ordinary parenthesis for denoting GCD. Now we use square bracket for denoting LCM of A and B. So LCM of A and B actually exists. Now we are going to make the definition precise. let A, B be positive integers, then LCM or least common multiple of A and B is 1. A multiple of A and A multiple of B, that is, it's a common multiple. That is, if L equal to LCM of AB, then L is a multiple of A, means A divides L and B divides L. This is the first condition. Second condition is if C is a multiple of A and B, then since L is least, then L is less than or equal to C. That means LCM is less than or equal to any other common multiple of A and B. These are the two defining conditions of the least common multiple of positive integers A and B. We will see an example now. The question is to find LCM of two randomly chosen numbers 15 and 20. So we will write down the multiples of 15. So that set we denote as M15. That is equal to the first multiple of 15 is going to be 15 itself. Next is 15 into 2, that is 30. Next is 15 into 3, that's 45. Next is 60. Next is 75, and so on. Okay. Now multiples of 20 are 20 itself. Now it is 40. After that it is 60. After that it's 80, and like that. Now if we take the intersection of multiples of 15 and multiples of 20, we see that the intersection is starting with nothing else, 60 here, and some more elements after that. So definitely the least element is going to be this 60. Therefore LCM of 15, 20 is equal to 60. We can find the LCM of two integers easily by the prime factorization, the canonical decomposition, because of the following reason. Finding LCM using canonical decomposition. Okay, for that, suppose we write the canonical decomposition of A like P1 to the power A1, etc., Pk to the power Ak, and of course this is not actually canonical decomposition. This is slightly different. B as P1 raised to B1, etc., Pk raised to Bk. We know that given two integers, it is not necessary that they may have any prime factors in common, or they will be having all prime factors in common. To avoid this problem, to avoid this confusion, what we usually do is to make the primes appearing in both the integers same. So we will permit that if some prime is not appearing in one of the numbers and it is appearing in the other number, wherever it's not appearing, you will write that prime to the power 0. Therefore here 0 less than or equal to AI BI. That's a condition. We are not asking for strictly positive A and BI. So that we have made A and B consisting of the same primes. Okay, now let L is the LCM of A and B. Therefore L is a multiple of A and L is a multiple of B. Therefore A divides L and B also divides L, and L is the least, having this property. So since A divides L, we know that A is consisting of factors, prime factors P1, P2, etc. up to Pk, and therefore clearly P1 raised to A1 divides L, P2 raised to A2 divides L, etc. Pk raised to Ak divides L. And similarly, P1 raised to P1 divides L, because it's a multiple of L is a multiple of all these factors. P2 raised to P2 divides L, etc. Pk to the power Pk divides L. Okay. So P1 to the power A1 divides L means that the power of P1 appearing in L is at least A1. So the power or the exponent of Pi appearing in L must be greater than or equal to Ai, because Pi raised to Ai divides L. Similarly, exponent of Pi in L must be greater than or equal to Pi also, because Pi raised to Pi also divides L. Therefore, exponent of Pi in L is greater than or equal to, if it has to be greater than or equal to both, then it has to be greater than or equal to maximum of Ai Bi. So this is the case for all the Pi's. Now, if we take some L dash to be equal to P1 to the power maximum of A1 B1, etc. Pk to the power maximum of Ak Bk, then definitely P1 to the power A1 and P1 to the power B1 divides this L prime, etc. Pk to the power Ak and Pk to the power Pk divides L prime. Therefore, A divides L prime and B divides L prime. We have already seen that for L to be the LCM, for something to be a common multiple, this is not actually required here. This is not really required here. If L is a common multiple, this is more than enough. If let L be a common multiple, and that's more than enough. Let L, we are just removing this, be a common multiple of A and B. This is more than enough. So A divides L, B divides L, etc. So if we take, so if L to be a common multiple, it is necessary that the least power of Pi appearing in L is maximum of Ai Pi. Now if we take L to be equal to, L prime is not necessary here. If we take L to be equal to P1 to the power maximum A1 B1, etc. Pk to the power maximum Ak Bk, note that this is the least power of P1 required in a common multiple. This is the least power of Pk to the power maximum of Ak Bk, that is the least power of Pk required in a common multiple, and the least power we have considered here. Since we have considered all the least powers of primes appearing in A and B in L, so A will be definitely dividing L, B will be definitely dividing L because of the previous discussion, the above discussion. Therefore, there is no other possibility that anything else less than L is going to be a common multiple because of the prime conditions. Therefore, L is the least common multiple, because the justification is the following: if some number, if A divides L and B divides L, that means L is a common multiple of A and B, then Definitely the least power of pi requiring in L is maximum of AIBI. So if we take something more than maximum of AIBI, that also will be a multiple of A and B, but that is not going to be least, because the least, the condition is it is equal to maximum of AIBI. If it's something more than maximum of AIBI, then it's going to be not the least but something bigger. So to get the least common multiple, we take whatever is the least power that we need to choose of pi in L, we are taking exactly that. So we get LCM of L equal to p1 to the power maximum a1 b1 etc pk to the power maximum ak bk. So using canonical decomposition and in fact a general version of that, we see that we can find the GCD using the prime, finding out the prime powers appearing in A and B. We will see in the following problem how to make this work. So the question is to find the LCM of 90, 168 using canonical decomposition. So to find the canonical decomposition, we have to just split 90 and 168 into prime factors. So 90 from the first observation, this is 30 into 3. Now we can further split it down. 30 is nothing but 3 into 10. So 3 into 10 into 3. Now 10 is 2 into 5, that is the least. 2 into, so 3 square into 5. That is the canonical decomposition here. Now 168 is going to be, that we can see that it's a multiple of 4. Therefore 4 into, this is 42, this is equal to 4 into 2 into 21, this is 4, 2, that is 2 cube, 2 cube into 3 into 7. So if you want, we can write a 7 to the power 0 here, or 5 to the power 0 also here. So 90 is equal to 2 to the power 1, 3 square, 5 to the power 1, 7 to the power 0, and 168 equal to 2 to the power 3, 3 to the power 1, 5 to the power 0, and 7 to the power 1. Therefore, if we take the maximum of the powers, the LCM is 90, 168 equal to the maximum of 2 to the power maximum 13 into 3 to the power maximum of 21 into 5 to the power maximum of 10 into 7 to the power maximum of 1. So finally we get this equal to 2 to the power 3 into 3 to the power 2 into 5 to the power 1 into 7 to the power 1. This is the final answer. We can multiply and find out the final answer here. One more question which I am leaving as an exercise. Find the LCM of 1050 and 2574 using canonical decomposition. This is an exercise. So write down the prime factorization of 1050 and then the prime factorization of 2574. Then take the common primes and take the, not the common primes, then take the prime powers and take maximum of prime powers to get the LCM. Now another observation we are going to make. We have seen that if A equal to P1 raised to A1 etc Pk raised to Ak and B equal to P1 raised to B1 etc Pk raised to Bk with 0 less than or equal to Ai Bi, So we are permitting some to make the primes appearing in both these numbers the same. We are permitting prime power to be equal to even 0. Then we know that GCD of A and B, this is equal to P1 to the power minimum of A1 B1 into etc. into Pk to the power minimum of AK Bk. Now the LCM we have just now observed that this is equal to P1 to the power maximum of A1 B1 into etc. into Pk to the power maximum of AK Bk. Now observe that if the minimum of AI Bi is equal to Ai, suppose, then what about the maximum? If one is minimum, if two numbers are given, if one of them is the minimum, then the other is going to be naturally the maximum. Maximum of AI Bi is going to be equal to Bi. Therefore, if we take the product of these two, here we have minimum of A1 B1, here we have maximum of A1 B1. So if A1 is appearing in the minimum, B1 will be appearing in the maximum. If B1 is appearing in the minimum, A1 will be appearing in the maximum. So minimum of A1 B1, maximum of A1 B1, together they will give A1 and B1 both. So AB into the LCM, GCD into LCM is nothing but P1 to the power A1 plus B1, because one of them is minimum, the other is maximum, into etc. into Pk to the power AK plus Bk. And if we split this is P1 to the power A1 into etc. into Pk to the power AK. Now again P1 to the power B1 into etc. into Pk to the power Bk, and this is nothing but A into B. So we have verified or proved that the product of LCM and GCD of two positive integers is equal to the product of the numbers itself. So we are going to write the question, the answer of which we have already explained. So the question is the following. Show that if A and B are two positive integers, then GCD of AB into LCM of AB is equal to the product of two numbers. This is an exercise. And now we have an immediate consequence also. This can be verified easily. If A and B are positive integers, see here AB, GCD into LCM is equal to AB. So to find LCM, then LCM of AB is nothing but the product of A and B divided by GCD of A and B. So since we know that there is an algorithm for finding the GCD of two positive integers, the Euclidean algorithm. So once we find the GCD and the product of the two numbers, we can easily find the LCM also. So this is also an exercise. So this is quite straightforward. Once we prove the above thing, we have to just take GCD of AB to the right side, and it should be brought to the denominator of AB. Prove it. This is the question. Now we are going to use this for finding the LCM. Find GCD of 252 and 360, and hence compute LCM of 252 and 360. Okay, we will find the GCD using Euclidean algorithm. Of course, we can find using the canonical decomposition also. Either way, we have to find the GCD. So this is 252 into 1 plus what is remaining? 108. Okay, now we continue. This is using Euclidean algorithm. So 252 now, this is equal to 102, we can take 2 times, 108 we can take 2 times, plus this is 36. Now 108 is equal to 36 into 3 plus 0. Therefore, this is the GCD. So GCD is now found. So GCD of 252, 360 is equal to 36. Now what about LCM? LCM of 252, 360 is equal to, from the above result, this is equal to the product of 252 and 360 divided by the GCD 36, and this is nothing but 36 360, therefore this is 2520. So we computed the LCM using GCD. Now we are going to see what happens to the LCM when two numbers given are relatively prime. So suppose A and B are relatively prime, or GCD of AB equal to 1. That is AB relatively prime or pairwise coprime. So if AB is equal to 1, by our previous result we have AB LCM is equal to AB by GCD, therefore this is equal to AB. Therefore if A and B are relatively prime, then LCM is going to be equal to just the product AB. Now on the other hand, if LCM is equal to AB, but we know that LCM into GCD, we know that this is equal to the product. So here we are getting LCM itself is equal to AB, therefore GCD must be equal to 1, or A and B are relatively prime to each other. So the question is the following: show that GCD of two numbers A and B, where A and B are positive, is equal to the product of two numbers if and only if they are relatively prime. A and B are relatively prime or pairwise coprime to each other. Now we are going to define the LCM of more than two numbers, just like we did it for the LCM of more than two, the GCD of more than two numbers. So our definition is the following. It's a recursive definition. Suppose, or let A1, A2, etc. AM be positive integers. Then we define the LCM of A1, A2, etc. AM recursively in this way, equal to LCM of A1, A2, etc. AM minus 1 and then AM. That means to find the LCM of three integers, we need to find the LCM of the first two, then take the LCM with the third integer. So example, LCM of A1, A2, A3 equal to LCM of A1, A2, then find this LCM and then find the LCM of that number and A3. So using this, we are going to solve the next problem. Evaluate 24, 28, 36, 40, the LCM of these four integers. So according to what we have written here, the LCM of 24, 28, 36, 40 is nothing but this is equal to LCM of 24, 28, 36 and then 40. Now we need to find the LCM of these three. So instead of finding the LCM of these three, again we are going to split 24, 28, 36. The LCM is nothing but this is equal to 24, 28. The LCM of these two and together with that 36. Now we have to find the LCM of 24 and suppose that this is expression 1, this is expression 2. Suppose that then we have to initially find the LCM of 24 and 38. So step 1, find 24, 28, the LCM. To find the LCM, we know that this is equal to the LCM of 24 and 28 is nothing but this is equal to 24 into 28 divided by GCD of 24, 28, and finding the GCD in this case is quite easy because we know that 24 and 28 shares the common factors 1 and 4, and 28 has the another factor 7, but that is not a factor of 24. Therefore finding GCD of 24 and 28 is quite easy, that's 4. 24 into 28 divided by 4, that is equal to 6 into 28, and that is 168. Now step 2. So we have to use this 168 in expression 2 to find the LCM of 168 and 36. Find LCM of 168 and 36. For finding the LCM of 168 and 36, we need to find the GCD of LCM 168 and 36, and we are going to use the Euclidean algorithm. Using Euclidean algorithm, 168 is equal to 36 into 4 times, so this is 120, 144, so remaining is 24. Now 36 is equal to 24 into 1 plus 12, and now 24 is equal to 12 into 2 plus 0. Therefore the GCD of 168 and 36 is nothing but this is equal to 12. So 168, 36, the LCM is equal to 168 into 36 divided by the LCM of the GCD of 168 and 36. This is equal to 168 into 36. We have just now found the LCM, and that is equal to 12, and on multiplying we get this to be equal to 168 into 3, 168 into 3, this is equal to 504. So we found the LCM of 168, 36, and so here we have 168, 36, this is equal to 504. Therefore the LCM of these three integers is 504. So the three integers 24, 28, 36 is equal to 504 we have found. Okay, now what is the last step? So we need to substitute this 504 into 40. So the final step is find 504 40. So 504 40 we need to find the GCD first. So using Euclidean algorithm, 504 is equal to 40 into 12, so 480 plus 24. Now 40 equal to 24 into 1 plus 16. Now 24 equal to 16 into 1 plus 8, and 16 equal to 8 into 2 plus 0, so the GCD is 8. So 504 40 GCD is equal to 8. Therefore LCM of 504 and 40, we can take the product divided by the GCD 504 40, and this is this 8 and 40, this is 5. Therefore we get the final answer to be equal to 2520. So finally LCM of 24, 28, 36, 40 equal to 2520. Actually, in the case when small numbers are involved in finding the LCM, we can easily use the canonical decomposition instead of doing all this work. So we are going to see this alternate method using canonical decomposition. So 24, if we write the prime factorization, this is 8 into 3, that is 2 cube into 3. 28 is nothing but 4 into 7, that is 2 square into 7. After that 36 is nothing but 4 into 9, which is 2 square into 3 square. Now 40 is 8 into 5, which is 2 cube into 5. Therefore LCM 24, 28, 36, 40, we need to take the maximum of prime powers appearing in each and everything. So the least prime is 2. What is the largest power? 3, 2, 2, 3. So 2 to the power 3 into next prime appearing is 3, and 3 has 3 to the power 1, 3 to the power 2. So largest is 2. Next is 5, and 5 is appearing only in one of the numbers, so 5 to the power 1. Next is 7, 7 is also appearing only once, so 7 to the power 1. So if you multiply, we will get the LCM. This is going to be very easy if the prime factorization is easy, but not that. When we have large numbers, this prime factorization is going to be quite a difficult task, and therefore we may have to use the Euclidean algorithm for finding GCD, and then use the relation between LCM and GCD. We stop here now, and we will continue with more properties and problems on LCM in the next session. Thank you.